right, let's get started. Although I'd like to figure out how to get some more light on in this room. It seems very gloomy. Ah, there we go. Now it's suddenly turned on. All right. So first of all, if anyone is watching on stream, I've tried reducing the frame rate and the encoding quality on the stream in order to lighten the load on this laptop. So if that makes the stream sort of unusable, please let Leo know on Teams, and he will hopefully be able to let me know, because I can't see what the actual stream looks like. All right, so let's first just recap what we were talking about last week on Friday. So we're talking about the set abstract data type, which is the sort of data type that encodes a set in the mathematical sense, a mutable set. So our interface allows us to add values to a set, check if a value is contained in the set, and to remove values. And we looked at an implementation of sets using hash tables. So remember that a hash table, we did a separate chaining hash table. So a hash table uses a hash function to essentially partition all the possible keys that we can put into the set into buckets. Each bucket is just an unordered list of elements or keys that fall into that bucket. And we looked at sort of how to make this efficient by resizing the hash table so that we try to keep the size of each bucket limited, because that way we can sort of, if the hash function is good and distributes the keys evenly by sort of doubling the size of the table every time we need to, we can keep the computational cost of insertions and lookups in amortized constant time. All right, so for today, all we're going to do is have a look at a different way to implement a set, and doing it using a tree instead. So what's a tree? I'm assuming that you know this from sort of discrete mathematics. A tree is a recursively defined structure where a node is a tree, and a node has some associated value and a number of children or subtrees or whatever we want to call them, and each of those is a tree. Right. So nodes that don't have any children are called leaf nodes, and because we're using this to implement a set, we don't have any duplicated values. But I suppose that in general you could have a tree where you have duplicated values, of course. However, you don't have any duplicated subtrees. That's an important part of the definition of a tree. So for any pair of nodes, there is always a unique path from one to the other, which is that you go sort of from one node up to their nearest common ancestor and then down to the other one. So it's never the case that you have two sort of different branches of the tree that then converge into a common node, because then it's no longer a tree, right? So the types of trees that we will be using for implementing a set are more specific. They're binary trees and they're binary search trees. So what that means is, first, binary, every node has at most 2 children. It can have 0 children or 1 child, but at most 2 subtrees. And the keys within the tree are ordered somehow. So they are ordered such that for every node, all the keys that are in its sort of left subtree are less than the key that is stored in that node, and all the ones that are in the right subtree are greater than the key that's stored in that node. So this assumes that we have an ordering of the keys that we are storing, and it assumes that we have a total ordering so that there are never two different keys that are not ordered, unless they're equal, right? And if they're equal, we don't store duplicates. So, but before we go into sort of how to implement a binary search tree, we need again to do a little detour and talk about ordering, how to order stuff in Java. So the Java standard library defines an interface called comparable. And the comparable interface has just a single method, which is called compare to. And what it does is implement, or it's meant to implement an ordering on elements. So if you call compare to on an object A with some argument B, which is another object of the same class, I suppose it doesn't have to be the same class. You could define an ordering that allows you to compare objects to objects of other classes as well. It returns an integer, and the idea is that you're supposed to return a negative value if A is less than B, a positive value if A is greater than B, and 0 if they're equal or not ordered. Or we should say 0 if they are not ordered, because you can implement a partial ordering. But if they are equal, then they are also, of course, not ordered. So again, let's have a look at what that looks like. We'll take. So again, remember last time we looked at the two different versions of equality, and we compared sort of equality for built-in data types like strings versus a class that we define. So we can also look at how ordering works here. So let's say we take two strings, and now maybe we should bring that up. API application. Let's find, is it this one? I think. Let's find the string and have a look at string. Where is string? Here's string. So you can see here that the string class implements the comparable interface. And actually, let's have a look at the comparable interface. So you can see that the comparable interface is generic, so it's typed. So you can define comparable for different types. And the string class is comparable to strings, which means that you can only compare strings to strings or strings to subclasses of strings, right? If you were to subclass string. Let's see. It's not documented here. So let's go back and have a look at this again. So in here you can also find a bit more sort of documentation of what the compare to method is supposed to do, but it's pretty much what I just said. Right. So let's, like I said, let's try this with strings. So we have two strings, and let's say And we'll take both of them just to see. And also look at P2 compared to P1. Run that and see, is it any faster? Oh, come on. I'm going to complain about that. Just because oh, actually, okay, let's just do this then. Just comment out the entire contents of the file. Alright, cool. Then we can run our equality test. Okay, so now we see that compare to returns 0 for both comparisons, which you would expect because we had set the strings to the same value. So let's compare two different strings, let's say John and James or something like that. Then we should get something else. Right, so we see that we get some number. To be honest, I don't know why it's 14 and not 1 or some other number, but the important thing here is the sign, right? So we see that P2 compared to P1 is negative. That's because P2 is less than P1 according to this ordering on strings, whatever ordering strings define. And of course the converse, P1 is greater than P2, so we get a positive value. And I'm guessing here that the order is pretty much alphabetical, right? So James comes before John in alphabetical order. And of course, because this is an ordering of strings, so it orders sort of all strings that are different. So let's try John with capital and lowercase. And as you would see, you do get a difference. So P1, so John with a capital J, is less than P2, John with a lowercase j, and that's just because the ordering of characters is based on their Unicode values. Well, actually, I'm not sure if it's Unicode, but their sort of corresponding numerical values under whatever character encoding scheme is used here. And the capital letters come before the lowercase letters in pretty much all standard encodings. So that's just how the compare to method works. So we've seen here that strings, for example, and probably most other classes in the Java standard library implement a comparable interface. They have a compare to method that does hopefully something reasonable on that class. But if we define our own classes and we want them to be comparable, then we have to implement a comparable interface. So again, just to sort of demonstrate, let's say we take our person class and we have two people here. Now this happened to be two identical people, but we can change it to be two not identical people, say an old John and a young John. And we can run this. Now this is going to complain because we haven't implemented compare to, and unlike equals and hash code, there is no default implementation of compare. So remember that for equals and hash code, you inherit a default implementation from the root class object, but for compare to, there is no default, so you have to implement one if you want to have one. So let's have a look at person. So So here's a simple implementation of compare to for person. So first we compare the names. If the names are different, then we return whatever the comparison on the names is. Otherwise, we compare on age, right? So let's say age minus other, which means that this will be negative if our age is less than, so we'll order them first alphabetically on names and then by increasing age, right? That's how this will work. Now this is going to complain again because we have labeled this as an override and we haven't said what it overrides. So we have to say that this is actually implements comparable, right? So we have to say that this class implements comparable of a certain type. And in this case, we'll put the type here to be the same as the class. So note that, for example, if we had something more general than person, I don't know, vertebrates or something like this, we could put any sort of superclass of person or indeed anything else here. So this is just defining what we are allowed to compare a person to. So it's defining what is the class that the argument to compare to can be. So typically you would have something that at least includes the class that you're defining the interface in or implementing the interface in, but you could actually have something completely different. So you really can compare apples and oranges if the apple class implements comparable oranges. Alright, so now we have implemented our compare method and defined that it implements the interface. So we can try this again. And now we see that, well, first of all, that it works and that we get the expected result that P2, which is, let's see, when do we have a test? Yeah, P2, which is young, Yon, is less than P1, or P1 is greater than P2. Right. So that's how we deal with ordering in Java. Now, with that in mind, we can go back to actually implementing our binary search tree. Right. Or rather, implementing a set using a binary search tree. So, so we need to implement the interface. So there we have something that will at least compile. So to implement a binary tree, we'll need something that represents nodes in the tree. So we go back to our definition of a tree. So remember that a tree is recursively defined in terms of nodes. So a single node is a tree, and a node with subtrees is a tree. So we will probably need to define some sort of inner class to represent the node. Let's call it node. And our node will store a value and it will have, because this is a binary tree, it will have at most 2 subtrees, a left and a right. So the value is something of type T, because we're writing a generic set implementation, and the left and right subtrees are references to nodes, right? So probably looks something like this. Then we need to fill this in with a few things, constructors, etc. Not entirely sure, but I'm going to guess that we will need the constructor to provide a value. We're always going to construct nodes that have a value. So we'll just initialize the value and maybe leave the subtrees to be null. And we might want to have some other utility methods in the node class. I'm not entirely sure. But we'll figure that out. We'll add them as we find out that we need them. Right, now the actual set itself will also need to have something in it, some fields. So first of all, we will need to have the actual tree that we're storing things in. So as we said, this will be a node, and we call it a root, just because that's the terminology of trees. The tree starts with a single root and it ends in many leaves. Although we always draw them from sort of with a root on top, so they're like upside down compared to actual trees. And also we might do the same as we did for the hash set and track the number of elements that we have stored separately, although we could of course always traverse the tree and count how many values are in it, but we might want to track them just for simplicity. What do we call it? Number of elements or something like this. Before I forget, so that means that the size can just return the number of elements. Right, so if we want to add something into our tree, now this is where it gets sort of complicated. How are we going to add something into the tree? So because a tree is sort of recursively defined, we will probably use a recursive function here, and I'm just going to guess that it might be easier if we split this up into some sort of utility method on the node class. So let's just put something on here. A new value. Maybe we should call it new value or something to distinguish it from the current value. So, assuming that we have a tree and we want to add a new value into the tree, how are we going to go about this? So we're looking at a node, and remember that the property of a node here is that in a binary search tree is that the left subtree contains only keys that are less than the key in this node, and the right subtree contains keys that are greater than the key in this node. So we are going to compare the new value with the value or key. Maybe we should call this key instead of value because we're mixing the terminology here, but now it's called value. So we're comparing the value with the value that is stored in this node. Let's just see. Okay, all good. Okay. So now this is complaining here a little bit. And why is it complaining? It's complaining because we haven't said that the type must be comparable. So is it okay to do that? Or do we actually have to say comparable t? No, we don't have to, I think. It's just comparable. Should be enough. Let's see, is this still complaining? Okay. Again, it's complaining about the fact that we have to make all the interface methods public. So let's do that to get rid of the warnings. There we go. And somewhere we're missing a return statement, but that's because we haven't finished writing this yet. Yeah. Alright. So we're comparing the new value to the value that is stored in this node. And we have three possibilities. It can be less than, it can be greater than, or it can be the same, right? So if the comparison is less than 0, that means new value is less than this value. Oh no, sorry, the other way around. Because we're doing, that means this value is less than, okay. So we'll do it that way then. If it's greater, then new value is less than this value. So in that case, what we should do is insert into left subtree, right? Because all keys that are smaller are going to go in the left subtree and greater in the right subtree. All right. Okay. Less than 0. Out, and if the comparison here is less than, then new value is greater than this value, so then we should insert it into the right subtree. Yes, sorry, have I switched something?
How do you know that t is comparable to itself?
That is a good question, and we don't. Actually, this is what I was wondering, if it's okay to just say that it's comparable, or if we should actually specify that it should be comparable to itself. At least, I mean, to be honest, I'm not sure which one of these two is acceptable Java syntax, or if both of them are. If we don't specify it, then I'm guessing what would happen is that we would get a runtime error, a class cost exception, if the type T actually did not implement comparison with itself. Because we are definitely going to be comparing it with instances of itself here, so if that's not what it's able to do, we would probably get a runtime error. But it would be interesting to know if we can say that it should be comparable to itself. So let's leave that in there. At least the IDE is not complaining. And final case, so if the comparison value is not greater than, it's not less than, then it's equal. And then that means new value should equal this value. So again here we're making an assumption that all of the things that we're inserting into the types that we're storing in this set is totally ordered. So all values that are not equal have an ordering, right? So we might actually want to assert that that is the case. So if the comparison value is 0, then we should have this value equals new value. Right. Alright, but let's come back to the two sort of recursive cases. So if we want to insert something into the left subtree, how do we do that? Well, first of all, what we need to do is see, do we have a left subtree? Right. If our current left subtree is null, then what we'll do is just create a new subtree here. And that new subtree will just consist of a single node that stores this value. Right. So we'll do a new node with the new value. And otherwise, what we need to do, if we already have a subtree there, well, then we will recursively add this value into that subtree. Because we don't know where it's going to end up in the subtree, but it will be somewhere in the subtree, so we'll just add it. So we'll just say left add new value. And the case for going in the right subtree is the same, just with right instead of left. So if right is null, then new value, otherwise recursively add it. Now, there's just one little outstanding thing here, which is that I made this method return a boolean, and there was an idea with that. And the idea was that we will return true or something like this if we actually added the element, and we'll return false if the element was already in the set. And the reason for that is just that so we can know whether or not we should update the count in the main add method. So to implement that, we will need to, in this case, well, where we do a recursive call, we need to return the value of the recursive call. Where we create a new node, we will definitely need to return true. And in the case where we already found a value, then we will return false. Okay. So then our main add method will look something like if root add element, then add +1 to number of elements. There's one more little detail here. There's a special case to deal with, which is if we have 0 elements in the tree, because then we don't have a root node. So we might have to have a special case for that. If root is null, then what do we need to do? Then we need to create just a single new node with the key, and then set the number of elements. So new node and set number of elements to 1, because now we have just added 1 element. Alright, so if that compiles and all is good, let's run just a build to see what happens. Yeah, okay, so that compiles. Now we can go back to testing. Right. Okay, we have some. Okay. So remember that in the test class, we just have to substitute here what we create when we create an empty string. Okay, so we can do sets of strings here, and it's so clever that it figures out that we need to import our. Okay. So we should be able to run at least the first test case here, which was just creating and checking size, right? So let's try that. Yep, and this was all working. The create and add test works. So next we need to then implement contains and remove in order to be able to do the other test cases. Right. So contains is pretty straightforward given the template that we've already seen. So the contains function will look almost exactly like this recursive add function that we did for the node, except that we won't add something if we come to a point where it should be, but it isn't. So we'll just copy that one and do sort of a little util method here. We might be able to do this in a nicer way by having just a general recursive method for finding the node where a value should be, and then using that in both add and contains. But for now, we'll just do separate implementations. So the contains method does the same thing. Shouldn't really call it new, but anyway. So we compare, it should be, so we shouldn't say insert because we're not inserting. So if the new value or the value that we're looking for is less than the value of this node, then if the value that we're looking for exists in the tree, it will be somewhere in the left subtree. Right? So that means that if the left subtree doesn't exist, so this is a leaf, or at least there's nothing there, then we know that this value does not exist in the subtree or in the tree. So that's the case where we will return false. And otherwise, we have to, again, recursively search the left subtree. Right? And same in the other case on the right. If the right subtree doesn't exist, well, then we return false, and otherwise we recursively search the right subtree. And in this case, where the order value is 0, well, according to our assumption of total order, they should still be equal. But in this case, we want to return true because this is a contains check, right? So that should pretty much take care of contains. Again, we'll need a special case. If the root node is null, then we have an empty tree, so we can definitely return false. It will not contain the element. And otherwise, we will just call contains on the root element. All right, so that should allow us to test at least the add and contains. No, it didn't work. Okay, we got something wrong. Uh-huh. So, we have a bug somewhere in our implementation because we're failing this test. So we added a couple of things and we looked up a couple of things, but this did not produce the expected result. So this should be true. We have added a bunch of vegetables, carrot, cabbage, broccoli, etc., including rocket, and we're checking contains for rocket, and this is returning false, but it should of course be true. All right, so let's see. Let's start by simplifying the test case and see. Yes. Oh, okay. Well, someone already pointed out the error. So, but anyway, let's just to see a little bit of what we might have otherwise done. First thing we could do is to simplify the test case, just to see, produce sort of a minimal test case that has the same problem. Right. So let's just add two elements. The first one, because we're testing containment for that one first, and then the second one. Right. So let's run the test again just to see what happens. So we still get the same error here, which means that we have a very simple little tree, and which contains only two elements. We could work out what is this tree supposed to look like after we add the two elements. Well, first we add carrot, so carrot becomes the value at the root node. Then we add rocket. Rocket is alphabetically greater than carrot, so we add it to the right subtree. At this point, if we couldn't figure out the error, it might be a good idea to implement the toString method, because that would allow us to visualize what our tree looks like at different points. So actually, let's do that just to see what things sort of look like. So again, we're going to do the same thing. We'll just implement a recursive toString method in the node class and just call that from the main toString method. And I suppose that will be equals write that if left is null, then empty, otherwise left. String, yeah. And so we'll just recursively convert left and right subtrees to string if they exist. If they don't, we'll just put a string empty to signify null. And then we'll just return something like, I don't know, we'll do brackets left, comma, to string, comma, right, something like that. And again, we have to do a special case for the root being empty. So if root null, return just I guess empty. Otherwise, we'll return root to string. Should have a return here. All right. So that's our toString implementation, and then we might do something like every time we add something, we'll print out the current tree. So all right, and then we'll run our test again and see what comes out. Doing here. All right. It has to be public. All right. So we can see that the when we run this test case, after the first insertion, caret, we have what we expect. We have empty left and right subtrees. Caret is the value of the root node. After the second insertion, we have, again, rocket stored in the right subnode, or the root node of the right subtree, which again has empty left and right because there's nothing else in there. So it looks like our set construction is correct here. We're not seeing any error in the creation of the tree, right? So that would lead us then to believe that maybe the error is in the contains method, which, as was pointed out already, it is indeed, the error is here, that the basically a copy paste there. We're calling add instead of contains on the right subtree case. So with that fixed, no, still not working. What did we get wrong this time? Okay, but that's because we modified the test case. Right, so we'll put back our original test case. And try that again. Alright. So now it's working, and of course now we can also see when we look at these, when we construct the trees, since we print them out, we can see sort of what they look like. That's a pretty small one, but yeah. Alright, so the final piece that we have to implement of the interface is the remove method. So if we want to remove something from the tree, this will be a little bit more complicated, because so in the add method, all we needed to do was to basically find a place where we could insert a new leaf node. We always add things at leaf nodes, but remove might be a little bit more tricky, because we might need to remove interior nodes, right? So probably easiest if we sort of go back up and again do a recursive implementation of remove. what should we call it? Value. That's not it. R value. Value to remove. So now, if we want to remove something, again, we sort of have to think about the cases that we have. We're still going to start the same way, right? We're going to compare the value that we want to remove to the value that is stored at the current node. So we're going to say, again, we'll do compare to, say, this value compared to the value to remove. And we have sort of a similar situation as before. So again, let's see if this is if C is greater than 0, that means then that our value is in the left subtree if it exists. And if C is less than 0, and the final case, which will be that it's equal, right? And in that case, well, again, we're going to do the same assert, just to double check, they should be equal. If the order is 0, then they should be equal. So this is the interesting case now. This is where we have found a node that actually contains the value that we want to remove. So how are we going to do this? So that means we need to remove this node from the tree, but we need to keep any subtrees that that node has, right? So let's see how we're going to do that. So again, let's sort of think by cases. So let's say if this node doesn't have a right subtree, then it's straightforward, because then when we remove this node, all that will happen is that it will be replaced by its left subtree. So essentially here, because we're missing a right subtree, which means we just have sort of a linear chain of nodes, which means that we can just take out one node and insert whatever is on the left in the same place, right? So then in this case, we can just sort of drop this node and move left up by 1. So that sort of suggests that what we actually want to do here is to return a node. So it will look something like, in this case, if the value to remove is in the left subtree, we're going to do some modification of the left subtree. Because we're modifying the left subtree, we might have to actually have a different subtree. So what we'll do in this case is to say that we will reassign left subtree to whatever is the new left subtree after removing the value from the left subtree, right? So go left, remove our value. So we'll update left in that case, and on this side, well, it's sort of analogous. If it's in the right subtree, then right is going to be right remove. So in this case, this becomes simple because if we don't have a right subtree, we're just going to sort of move the left subtree up, and which means we return left here. And same, if we don't have a left subtree, then we'll just return right. Okay, so those were the easy cases. And of course, this covers also the case where both of them are null. Right? Then we just return a null. Now, the tricky one is then if we have both a left and a right subtree. So let's see. We can go back and look at our illustration here. Right. So let's look at some example case where we have, let's see, what do we got? We have, let's think of an easy example first, which is where we have, let's say we wanted to remove banana here from this tree. Right. Banana has two subtrees. So if we remove this node, what will have to happen is that one of these two will sort of move up and become the replacement, and the other one will have to become a child node of the one that we move up. Because we can't put an empty node here, and we can't sort of smash them into just one. Somehow we'll have to join them together into one tree. So I suppose if we look at them, yeah, it doesn't really matter which one we move up, right? What matters is just that once we move one of them up, we have to insert the other one, which is a whole subtree, somehow in the right position in the subtree that we just moved up. So let's sort of just look at the two possibilities. If we say we take the left subtree and move that up, so then we cross out banana here, we put apricot, and then we have this subtree which we would insert into the apricot subtree, right? And now the nice thing is that inserting a subtree is not really more difficult than inserting a node, right? Because again, if oh no, actually it is. It is more complicated. It's really complicated because we're going to have to look at comparing not just the root of the subtree, but also the children recursively and finding the right place for them, right? So, so how does that work? We're going to have to, yeah, let's say if we want to insert this subtree onto here, we would compare the label or the key mango with apricot. Mango is greater than apricot, so it will go on the right. Okay. Now we know that everything that's on the right of mango will also be on the right of apricot. But the things that are on the left of mango, we don't know if they should be a left or right of apricot, which means that we have to take the left subtree here and sort of recursively then insert that subtree under the apricot subtree. So it does turn out to be somewhat complicated to do this, but we'll see if we can figure it out. So in order to do this, let's say that we create another little another helper method. Let's call it let's say it's a void, and it's going to be called insert, and it's going to be a subtree. So the idea here is that we are going to insert a whole subtree into this node. And we can give it an extra argument which is called root, but we'll get to why we have that in a moment. So, so here we're going to, again, we start off in the same way as always. We're going to compare the key of this node with the key of the root node of the subtree. Right. So again, we compare this value with the subtree's value, right? And if, same as always, let's see if c is less than, no, wait, if c is greater than 0, then subtree root goes on left, and if less than 0, you get that right again, then subtree root goes on the right, and otherwise they're equal. So let's look at the case where it goes on the left. So let me just double check, did we get this right again? Okay, so if this is greater than subtree root, then it goes on the left. Yeah, okay. So now, when we put the subtree on the left of this node, we know that the root key of the subtree is less than the key of this node, and we know that everything in the left subtree of the subtree is less than this node. But we don't know about the right subtree of the subtree, right? And that's our problem here, which means that we will now have to figure out where are we going to insert the right subtree of that subtree. So what we might have to do then is to, let's say, to take out that right subtree and then reinsert that from the top, where the top is the point where we decided originally to insert the subtree. So not the current node necessarily, but it could be somewhere above. So we'll call it sub-right, which is the subtree's right. And then the subtree's right, oh sorry, no, the subtree's right we are going to set to null. And then we are going to and that's why we have this root argument here, and we're going to insert sub-right there. Now we haven't quite finished up here, because we also need to actually recursively insert the subtree without its right branch on the left here, right? So we need to find the place where it should go, which means that we need to do, again, if we don't have a left, then that's easy. We're just going to say our left becomes the subtree. But if we do have a left, then we have to recursively go down the left and decide where we're going to insert what remains of this tree. Should we excise that one first? Probably, yes. Okay. So we're going to take out this right branch of the subtree, and then we're going to insert the subtree with its remaining left branch on our left. We go left, insert subtree, and then we're going to insert the right branch of the subtree from whatever point we started from. I think this might be correct. It could very well be very wrong. But we'll try it on this side again. So again, this of course is analogous. We're just going to take the left instead here and sub left. If we don't have a right, then we just assign it. Otherwise we go with right insert, and here we'll go sub left, right. Now the equal case is again a bit of a problem, because so if we want to if the key of the subtree is equal to this, it doesn't tell us anything about what the actually, well, in the case where we're using it, it should never happen, but the problem is we don't know anything about the subtrees again. So if the key is equal, what we know is that the left branch, or the left subtree of the subtree, is going to go on our left, and the right subtree of the subtree is going to go on our right, but we still would have to do those insertions. Now it's probably enough that we just do those, so we'll just go again, if we have a if our left is null, then our left will become the subtree's left. Otherwise we will do recursively insert. I think we've forgotten to put the root argument in everywhere. The left subtree on our left, and then analogous for right. Alright, so let's go back and fix the bugs here. What is wrong with that one? Was null, and same. And yeah, okay, here we just need to pass the root here and here. Alright, so right, so this was our sort of complicated case where we wanted to insert something, or sorry, where we wanted to remove a node and it has two children. Now, coming back to our illustration, what was it we wanted to do again? We wanted to now pick one of these two subtrees, doesn't matter actually which one, to become the replacement for the node that we're removing, and then we wanted to insert the other subtree into the one that we're replacing this node with, right? So we might just arbitrarily say that we go left insert, and here we go, we'll use then left as the root, and the subtree being our right. And then we return left. Right. So we take the left subtree, we insert the right subtree into the left, and then we just, now effectively we have removed the right subtree, so we just return the left as being the new root of this subtree. Right. Okay. Not entirely sure if this is actually working or correct, but but now in the actual remove method, we need to now we haven't checked here in remove if yeah, there's actually there's definitely an error here, because we don't actually check if we have a left subtree or a right subtree to recurse into. So here we should say if well, if left is null, that means the value to remove doesn't exist in the tree. So what do we do at this point? We just return ourselves this node unmodified, right? Because that means we're not modifying anything. And same here on the right. If right is null, we'll just return this. So okay, so that should complete that. But now we don't have a check whether something is actually removed or not. So we might have to do an if contains element. Then if the set contains the element, then we know that something is going to be removed. So we can update our counter minus equal 1, and then we'll just call root remove element. Again, we need to have our check just for null value. If root is null, well, then there's nothing to do, so we just return. Alright, that's probably not going to work, but we can test it at least. Let's see. Oh, we're missing a return statement somewhere. Where are we not returning? Ah, yeah. Yeah, okay. So we still need to return this. Yeah. So in the case here of the remove, where we update either the left or right subtree, we still need to return a node because we have defined it that we're returning something. So we update or we return the node itself. Alright, we'll try that again. Yeah. So as expected, our remove test isn't really working, but let's find out exactly where it goes wrong. Okay, because we're not checking for nulls somewhere. Okay, so here it's saying that if we can call this with a null subtree. Now, where do we do that? Well, so if we're going to insert a null subtree, then we don't have to do anything, right? So we can just return, and that gets rid of our null pointer error. Okay, so now we get yeah. So now we get more of the sort of error we expected to see, which is that the implementation is not working correctly. So specifically, what is failing here is that we add some things to the set, and then we remove something, and then we contains check after removing it, and it's still there. So again, let's see what happens if we simplify the test case. So we're just going to add one element, remove that element, and then assert that it is no longer there. Does that work? No, not even that works. Okay. So No. No. So let's make use of our string method so that we can see what things look like. So here we'll say, remember that we're printing the tree every time we add something, so we'll just say after add something like that. Right. So we'll say we'll see what the tree looks like after add and after remove. So after every modifying operation. Right. So what we can see is that, well, the remove is not working because, so after adding carrot to the tree looks like we would expect, but after removing it, it doesn't. So somewhere in our rather complicated remove function we have made an error. So, and it might even be as simple as right here, because remember that the does remove return something, or is it void? Hang on. Yeah, so remember that remove returns a node, which is an update, represents the updated tree, and when we call remove on the root node, then we should update the field root with the updated tree. So maybe that was actually the whole of it. We'll see what that does. Yeah. Yeah, okay, well at least now it's failing a different test, and that's because we've modified the test case. Alright, so we might come back and try the whole test case. There. Oh, and then it actually all works. So now I wouldn't be absolutely confident that this implementation of remove is actually correct, but at least it passes the tests that we have defined so far. And if we really wanted to try it out, we should maybe sort of define some more comprehensive test cases to make sure we're covering all the edge cases. Now there is one aspect here of the of this implementation that we haven't talked about at all so far, which is, why did we bother? You know, why did we do this binary search tree? And again, the answer is the same as for the hash table, right? Because of efficiency is the driving idea. And the idea is that if we have a nicely balanced binary search tree, then the path from the root down to any leaf is going to be of length that is logarithmic in the size of the tree. So, and that's important because when we look if something is in the tree, we have to sort of traverse a path from the root down to a leaf, right? It's only when we get to a leaf, or at least a node that doesn't have either a left or a right, then we can conclude that something is not in there, right? So, so the fact that the depth is logarithmic means that if we double the size of the tree, as in if it's a perfectly balanced tree, every time we double the number of elements in the tree, we only increase the depth by 1, right? And that means that in theory at least, as long as we keep the tree nicely balanced, we should have fast lookups. They should be logarithmic in the size of the size of the set, or at least do a logarithmic number of comparisons. So the problem is that with our current implementation, we're not doing anything to make sure that the tree is nicely balanced. Right. And in fact, we can do a little test here. Let's just do a little main here where we can test some simple things. So string. Let's say we add we can add something simple. We'll use the classics. Add Alice, Bob, add Alice, Bob, Carol. Who comes after that? Dave, I guess. Or something like that. Well, we'll do something like this. And let's find where is our list set, and then at the end we want to print the tree. Yeah. So we'll see. We're just going to add 4 names in alphabetical order, and at the end we'll see what the tree looks like. Let's run that. Right. So it's a little bit tricky maybe to read our string representation here, but you can see that the root node has Alice as the key, and it's got an empty left tree. And then the right subtree has Bob as the root node, or the key of the root, and an empty left subtree, and so on. So because we're adding these names in increasing alphabetical order, which is the ordering of the keys, we're just adding one on the right every time. Right. So we end up with a perfectly unbalanced tree, which is just a single sort of straight path down the right. And if we did it in, let's say, reverse alphabetical order, we would get a single straight path down the left. So in order to get sort of a balanced tree here, we would need to what we would want to do is to kind of insert something that's in the middle first, right? Because that will nicely split the list, and then we can insert, say, the 2 that go on the left and the 1 that goes on the right, or something like this. So again, let's see what that looks like. Right. So so here we can see that again. Of course, Alice. Oh no, why is that? Ah, yeah, okay. Oh no, okay. Right. Where is our root? So our root node here is Carol, and the left subtree here has Alice and Bob in it, as you would expect, and the right subtree has Dave, right? And then Alice and Bob, well, Alice, one of them has to be the root of that subtree. So because we're not doing anything here to ensure balancedness, the shape of our tree is going to be very much dependent on the order in which we insert things, which could be arbitrary. I mean, it depends entirely on the usage of the data structure. So what could we do about this if we wanted to sort of to address this situation? So there are algorithms for doing balanced insertion or rebalancing of a tree as you insert it. They're pretty They are pretty complicated. I wouldn't be able to implement one just off the top of my head, not having looked it up. But let's, with the little bit of time we have, let's start by just looking at sort of the statistics at how this behaves. So let's say that we will track on our nodes, we will sort of try to keep track of the depth, the maximum depth of subtrees. So in fact, maybe what we'll do is we'll track height instead. So height is defined as max depth of subtrees, or max. Maybe we should call it max height actually. Yeah, height. Typically, you define depth as sort of the distance from the root that a node sits. So conversely we'll call it height, which is the sort of the maximum depth that you can find underneath the subtree. So we can say that this is max height of subtrees, or equivalently max depth of any node below, right? So now when we create a node, it has a height of 0. Now we'll need to update that in some places. If we're going to, so we'll definitely need to update it on insertion. So in this case here, let's see, where we add a new node on the left, then, this is going to be an absolute pain, because we also recursively need to go up and track and recursively implement it. All right, we'll do it an easier way. We'll just compute the height when we need it, instead of tracking it. So. So we're just going to recursively compute the height of the left and right subtree. A null subtree has height 0 by definition, and then we will return the max of those plus 1. So that's just tracking sort of the height of our tree. So just to test that this is working, let's do so we really should, I suppose, we really should have a height method on the tree class itself, not just on the node, but we'll just cheat with that for now. And let's see what that does. Okay, so the height of this tree here is free. So the longest path is sort of has 3 keys on it. It's going Carol, Alice, Bob, right? So let's have a look at what happens if we insert something a little bit bigger. So we'll just copy this method over from hashset, where we read a file and insert all the keys in the file. Right. So well, it's not going to be hashset. It's going to be a txt set strings. Let's just check we haven't done any errors here. So right. So we'll have a look at here. We'll go set root. Fine. So every time that we add something, we'll print out the height, just so that we can, oh, actually we should probably comment out the other printouts just to not flood us with outputs. Tree after add, tree after remove. Alright, let's run that and see what happens. Alright. So, well, as you can see, I mean, in the beginning the height grows pretty quickly. Obviously, once we insert one or two elements, it's pretty much impossible to insert anything more unless we're really lucky. But yeah, it seems to be sort of, it's not growing too badly, but it still could be a lot better. So if we say, I mean, at the end we have a maximum height of, or maximum depth of any node is 17, which means we could potentially store 2 to the 17 nodes in this, which is, what is 2 to 17? That's, is that like 500,000 or 1 million or something? And we have actually stored 271. So we're not using this tree very effectively at this point. So if we wanted to try to fix this, instead we can try to do rebalancing when we insert, or we could do, in the same sort of similar way as we did with the hash table, we can do a periodic rebalancing of the set. So at some point when we think that the height has grown too big compared to the number of elements, we could try to essentially rebuild the whole tree using the current set of elements in it, but in an order that will make it sort of work, become more balanced. So I'm not sure if we're going to actually try to implement that. Probably not, with just 15 minutes to spare. So we'll put that aside and maybe put that into the lecture code on GitLab a little bit later. But the idea would be something fairly simple. We'll take out, say, we'll take the current contents of the tree, put it into an array, sort the array, and then insert starting with the middle, just to make sure that we balance it. or maybe not sort it. We could also just randomize it and hope that that ends up being in good order. I'm not sure exactly which approach would be better. All right, so we'll leave it there for today.